everyone, and welcome to week 3 Monday. So, this makes up for the class that we were supposed to have on Monday when we got snowed out. I have done this in two different sections just to make sure that it's not too long. Two different topics, two different sections. So, the first topic that we're going to talk about picks up right where we left off when we were talking about polar covalent bonds and how polar bonds can lead to polar molecules. So, this is just a reminder of what we've done. When two atoms have different electronegativities, and remember, electronegativity increases on the periodic table. Here's my, you guys know my periodic table, something like this. Electronegativity increases up and over. So fluorine is the most electronegative. Don't get too caught up in numbers. I know that a lot of books and a lot of websites might talk about difference in electronegativity based on numbers. Doesn't really matter. Just get a general sense that if it is over or if it is above, it is more electronegative. And I'm not sure I said this in class, but over counts for more. So, oh no, I don't actually have a periodic table right at my fingertip. Oh, I do. Chemistry professor. I got one right here. All right. So, just be like a little bit careful. Sometimes over and up like kind of gets a little bit confusing, but let's say like carbon versus phosphorus. Phosphorus is more electronegative. It pulls the electron density towards itself. That leaves carbon as partially positive, and the phosphorus is partially negative. Let's do like another one, like basically anything versus carbon. Like carbon versus chlorine. Chlorine is more electronegative. Chlorine pulls the electron density towards itself, leaving carbon as partially positive, and the chlorine is partially negative. All right, so those are polar covalent bonds. Remember, there is a gigantic exception. Huge. Carbon versus hydrogen is non-polar. They are totally in different locations on the periodic table. Definitely, it looks like carbon should be more electronegative than hydrogen. Totally agree with all of this, but it is just not true. The carbon-hydrogen bond is basically non-polar. All right, so now, if a molecule has polar bonds that are not symmetric, the molecule overall is polar. So think about it in terms of like you've got like a ring in the center and you've got dudes and or chicks like pulling on that center like ring in our tug of war. And let's say that we've got a big dude up here and we've got a big dude down here. And let's say that it's like this, but then you got a little wee baby little guy over there. All right. So the blue ones are the big dudes. They're the more electronegative atoms. They pull the electron density towards themselves. They're more electronegative. The electrons spend more time around them. This is asymmetrically like substituted around the center. It's asymmetric. You've got 3 big guys and 1 little teeny tiny guy. If all of these started pulling at the same time, we would absolutely get movement in this kind of direction. All right. This big guy here would kind of cancel out the lower guy here. Hopefully this is actually like recording my cursor. I think I clicked record cursor. But anyways, the guy on the top is canceled out with the guy on the bottom. But the guy on the right is not canceled out by the little greeny guy on the left. So this is asymmetrically substituted, and that asymmetry means that this molecule would be polar. An example of a symmetrically substituted. So again, let's say that we have a ring in the middle, and let's say this time we have 3 bonds. And we're going to put big guys at the end of all 3 of those bonds. We have 3 polar bonds. The big guy is more electronegative, pulls the electron density towards itself, etc., and so forth. But it is symmetric. The way they are put against each other is completely symmetric. All of those cancel out. The amount by which this points up is canceled out by the amount that that's pointing downwards. the amount that this is going to the left is canceled by the amount going to the right. So since this molecule is symmetrically substituted, the molecule overall is nonpolar. So if they cancel, nonpolar. If they don't cancel, polar. So let's do some examples. I cannot remember if we did carbon dioxide in class or not. I know I was kind of rushing at the end. Carbon dioxide is CO2. We're going to draw the Lewis structure of it first. Carbon is 4. Each of the oxygens is 6. So that's 12 plus 4 is 16. I don't have my calculator here either. I should have prepared better. We got 16 valence electrons. Carbon is the central atom. Bond to each one of the atoms. That takes care of 2 4 electrons. Fill in octets from the outside in. So 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. Okay, so we've got all of our electrons taken into account. We can't use any more. So now we got to say, well, carbon in the center is unhappy. It's unhappy because it's electron deficient. When you have an electron deficient atom next to atom with lone pairs, you have the opportunity for multiple bonds. So these mechanistic arrows say that this pair of electrons is no longer going to be isolated on the oxygen. Instead, it's going to be shared between. Same thing with this set of electrons. These electrons are going to move over, move down. I guess it's actually move up, and it's going to be shared between. So the full valid Lewis structure for carbon dioxide looks like this. All right, so that's sort of step one. Step one of this, like figuring out molecule thing, is you've got to draw the Lewis structure. So you got to know what you're doing to draw a Lewis structure in order to draw it properly. Now, step two is what is the bond? What is the molecular geometry? What is the shape around the central carbon atom? So again, you have to memorize this. Definitely want you to focus on the ones with 4 atoms and or 4 groups around the central atom, like tetrahedral, trig, pyramid, bent. Focus on all of them up to there, but don't forget about the trig bipyramid and the octahedral. I have some YouTube videos up about that, and if you want more YouTube videos about that, just let me know. So even though I have drawn this molecule looking like this angle, I need to get a red pen. Hold on one sec. All right. So even though this looks like I've drawn this, and so it has a bond angle of 90 degrees, so it looks like maybe it's a right angle, something along those lines. Remember, you got to be smarter than your drawing. It is not a 90-degree angle, not even close. We have a central atom, and it has 2 groups around it. Don't worry about counting bonds, count groups. So we have a central atom with 2 atoms around it. So remember, these things are just trying to get as far apart as humanly possible. The electron density that's in the bonds pushes the other bonds away from it. So how far apart can 2 things get? Linear. So the true drawing of carbon dioxide looks like this. Because now I am showing that this bond angle is 180 degrees. It is linear. So okay, so that's the second step. So we drew the Lewis structure. We figured out the bond angle. We redrew it so that it looked right to us. And now we have to figure out, all right, how many polar bonds are there in the molecule? There are 2. Each one of the oxygens is more electronegative than the carbon. So it pulls the electron density towards itself. That leaves carbon is partially positive, and each one of the oxygens is partially negative. Now, do they cancel? And the answer is absolutely yes. So again, if you've ever taken physics, or if you've ever talked about vectors and things like that, we have a vector going in this direction, which is equal and opposite the vector going in that direction. Those 2 bonds cancel. So since those bonds cancel, this molecule overall is nonpolar. So even though we have 2 polar bonds, the polar bonds cancel, and overall the molecule is nonpolar. All right, let's do another example. My friend water. Water is H2O. So again, like the steps that you need to take in order to answer the question, really the question that we're just asking right now is the molecule polar or nonpolar? All right, we're going to build up on that when we talk about intermolecular forces, but for right now, we at least need to know, is it polar or nonpolar? All right, so here's water. So we know what water looks like, but I'm just going to quickly go through those steps, drawing a full valid Lewis structure. Oh, one thing I forgot. I'm so sorry, friends. I forgot. We need to talk about the whole formal charges. Sometimes I like completely skip over the fact that we have to deal with formal charges. So again, hopefully you guys can see my cursor, but around this carbon, there's no formal charges. If I forget to talk about them, it's because there are none, just for future reference. But remember how I do it. We have carbon, that's in group 4, and we just count down every one that's around it. So we have carbon is 4, 3, 2, 1, 0. So carbon has a 0 formal charge. Around each one of the oxygens is group 6, 5, 4, 3, 2, 1, 0. So there are no formal charges. All right, so now here's water. Each one of the hydrogens has 1 valence electron, and the oxygen has 6 valence electrons. So that gives us a total of 8 to work with. Oxygen is the center atom. We bond to the hydrogens. That takes care of 2 4 electrons. We've got 4 more, and thankfully my oxygen is electron deficient and it needs them. So that is our full valid Lewis structure. There are no formal charges. Around each one of the hydrogens, hydrogen has is in group 1 rather. 1, 0, 1, 0. Oxygen is in group 6, so you count down 6, 5, 4, 3, 2, 1, 0. So that oxygen also has a 0 formal charge. Okay, so that's drawing the full Lewis structure. The next thing is, what is the shape around the central atom? And again, you've got to be smarter than your drawing. Your drawing suggests that this molecule is, again, linear. And I drew it this way on purpose just to really like send it home to you guys. I try to draw my molecules with shape. You probably don't. So I want you to be aware when you draw a molecule, you've got to double check the shapes. So around my central atom, I have 4 groups. I have 1, 2, 3. Well, I don't like that. Hold on. Let me 3, 4. So around my central atom, I have 4 groups. We have 2 atoms, 2 lone pairs. It's based on the tetrahedral, okay? Remember, I definitely talked about this. You have a central atom up and what I have right now to the left. Those are in the plane of the board. This thick wedge is trying to show it coming out at you, and the dashed is trying to show that it's going behind you. It's based on the tetrahedral, all right? But you can't see lone pairs. So I'm just going to erase those ones. You can't see them. The only thing you can see is atoms, right? Like electrons have basically no mass. So you really can't see something that basically has no mass. Also, electrons are zipping around and rotating. Anyways, you can't see them. So it's still based on the tetrahedral, but we can't see those lone pairs. Remember, they kind of are drawn like big paddles. So these atoms are not in a line. They are bent from each other. And the lone pairs of electrons take up more room, smushing this bond angle down to less than 109.5 degrees, 105. All right, so now the question is, and I'm going to redraw water so it looks better. So it's actually showing that geometry. The hydrogens are in the plane of the board, and we've got the lone pairs of electrons coming forward and going back. So now, got to figure out if it's polar or nonpolar. First question is, are there any polar bonds in the molecule? And sure enough, Oxygen is more electronegative than hydrogen. That leaves the hydrogens as partially positive, and that leaves our oxygen as partially negative. Positive, partial positive. Now that we know the Lewis structure, the shape, how many polar bonds there are, now we can say, do those polar bonds cancel or not? And again, it's like a vector. We've got a vector up to the left, we've got a vector up to the right. If oxygen starts pulling, this molecule's moving. There's no way those little teeny tiny hydrogen guys are going to be any match for big old oxygen. Since it moves, since those polar bonds don't cancel, this molecule is absolutely polar. All right. I will talk about these later. I'm going to give you, right, like if I were in class with you guys, I would be like, here are some molecules. Tell me if they're polar or nonpolar. Tell me about the shape around each one of the atoms. So if you want to go ahead and pause the video now, that's what I would recommend doing. I want to know, are the molecules polar or nonpolar? What is the shape around the atoms? So again, what I would do if I were you, I would pause, try to come up with some answers, and then you can unpause and see how you did. For me, I'm just going to keep going. Our first molecule over here, I'm going to call this guy molecule A. This is a molecule of ethanol. Ethanol is the alcohol that when you drink, you get drunk. So, first off, is the molecule polar or nonpolar? Well, in order to answer if the molecule is polar or nonpolar, you've got to figure out how many polar bonds there are in the molecule. There are only two. Remember, there is no electronegativity difference between a carbon and a hydrogen. So the only polar bonds we have are carbon-oxygen and carbon-hydrogen. The shape around that oxygen atom is bent, and this drawing is trying to show you that indeed it is bent. Now you got to say, do those polar bonds cancel? And the answer is no, they don't. They don't cancel because this is pointing down to the left, this is pointing down to the right. They're building on each other. So since the polar bonds do not cancel, this molecule is absolutely polar. And then just for funsies, the shape around that carbon is tetrahedral. It is tetrahedral because carbon has 1, 2, 3, 4 atoms around it, and there are no lone pairs. So that's 109.5 degrees. The shape around that carbon is also tetrahedral. This carbon here, I'll go to a different color. This carbon here has 1, 2, 3, 4 things around it, no lone pairs. So that's tetrahedral. And of course, our oxygen is bent and has a bond angle of 105 degrees. Over here, let's go to molecule letter B. This is a molecule of toluene. If you've ever used paint thinner, then you have used toluene. So taking a look at this molecule, the first question we got to ask ourselves is, are there any polar bonds anywhere in this molecule? And the answer is no. Since there are no polar bonds, this molecule is nonpolar. This has implications. We're going to come up with implications on this when we start talking about intermolecular forces. But one of the big things is that this molecule is not soluble in water. And I'll tell you that now so that when I get there, you'll understand. But if we go back and look at our water molecule, water's polar. Generally, generally, things that have the same intermolecular forces, the same, how do I want to say it? Generally, molecules that sort of look the same are going to be soluble in each other. So you can see water has oxygens bonded to hydrogens, and it's polar. This ain't got no oxygens in it whatsoever. It doesn't look anything like water, and it is nonpolar. That means it's not soluble. Ethanol, on the other hand, is soluble in water. You couldn't make things like Cosmopolitans, that's always my example. Cosmos are cranberry juice with vodka. And you couldn't make that into a mixture if ethanol wasn't soluble in water, because cranberry juice is mainly made up of water. The alcohol wouldn't dissolve if it wasn't soluble in each other. So this molecule is polar and is soluble in water. Because again, it looks the same. We've got this OH on there, same as what's in water. This guy, it ain't got nothing on it. So it is not soluble in water. Real quick, bond angles around this carbon here that is tetrahedral with a bond angle of 109.5 degrees. And every single one of the carbons in the ring, those are all trig planar with a bond angle of 120 degrees. You have a central atom with three things around it. So a central atom with three things, no lone pairs, is trig planar. Last but certainly not least, we have molecule C. This guy is dichloromethane. And we've got to figure out polar or nonpolar. So first thing is, what is the bond angle or the bond shape? And around this carbon, it is tetrahedral with a bond angle of 109.5 degrees. Central carbon with four atoms around it. No lone pairs on that central carbon. So it is tetrahedral. Again, we're trying to show this guy is coming out of the page at you. That one is fading away from you. All right, so we've got the Lewis structure. We've got the shape. Are there any polar bonds? Absolutely. We've got a polar bond, carbon to chlorine. Chlorine is the electronegative atom. That leaves carbon as partially positive. And we've got chlorine in the back as well. But now, do they cancel? And the answer is no, they don't. They build on each other. I hope that you guys see that they're building on each other. They're adding together. They're not canceling out. They're not subtractive. They're additions. So, since those polar bonds do not cancel, this molecule is polar. Interestingly enough, and again, we're going to come up to this implication here in a minute, even though this molecule is polar, it is not soluble in water. It doesn't look like water. There ain't no OH in there. Since there's no OH in there, they're not similar enough to each other. So, polarity isn't the be all end all in order to determine if a molecule is polar. Sometimes I feel like the biologists like to just bring it down to, is it polar? Then it's soluble. That is not always true. There are absolutely some molecules that are polar that are not soluble. Okay, so now we're going to get into, how do we know that? How can we use what a molecule is like in order to predict things about it? And we're going to start talking about intermolecular forces. I will always abbreviate intermolecular forces as the IMF. This is very, very important to me because an intermolecular force is not a bond. Okay, so a bond, let's look at water. A bond is right here. That's a bond. And what a bond really means is that you have two electrons shared between two atoms. There are electrons there. Those electrons are moving back and forth, spending time around the oxygen and the hydrogen. Now, it's a polar bond. It's a polar covalent bond. Two electrons are shared between the atoms. They're going to spend a little more time around the oxygen, but there are still two electrons being shared. That, to me, is a bond. When two electrons are shared. To be honest with you, you can have a one electron bond. Things get really weird when you have one electron bonds. But a bond, at the least, is when you have shared electrons. An intermolecular force, on the other hand, is what happens between molecules. So right here, we have water molecule A. It's got its own bonds and its own stuff happening. Over here, we have water molecule B. How these things interact with each other is the intermolecular force. Forces between two different molecules. Not a bond, just a force. All right, so there are three types. So I'm setting you up for success. There are three different intermolecular forces, and they go weak to strong. And the weakest one is called London dispersion. I'm going to explain them. I'm just setting us up for what's to come. So the London dispersion force is the weakest force. The molecules are not held together very tightly. There's not a whole lot of interaction or attraction between the two molecules that exhibit the London force. The dipole-dipole force, that's the middle force. That is stronger. They're getting more tightly held together. Hydrogen bonding, that is super strong. Molecules are held very tightly. If molecules are held together very tightly, so again, I'm talking about two different molecules. So there's molecule A, here's molecule B. And this is just because I can't do my hand motions because I'm not putting myself on camera right now. Anyways, since we have the red molecule and the green molecule, and let's say that they're hydrogen bonded to each other, that is held together really, really tightly. That's like kind of like what I'm trying to denote by the interaction in that I drew in black. They're held together very, very tightly. In order to get a substance to boil, to evaporate, to go into the gas phase, to undergo the phase change from a liquid to the gas, you've got to separate them. You've got to come in and break the two molecules apart, because after you break them apart, then they can go and celebrate being in the gas phase. Gas phase molecules are really, really far apart from each other, and they're moving around really, really rapidly. They can't do that unless they're pulled apart. So the stronger the intermolecular force, the more tightly those two molecules are held together, the more energy required to separate them. And so therefore, the boiling point goes up. Now, I really have to be careful here. We're not breaking bonds. Again, let's pretend that this is water. Water is H2O. Water is H2O. After we break the intermolecular force by adding in a bunch of energy to pull them apart from each other, it is still H2O. We have not broken a single bond. All we've done is taken two molecules that are attracted to each other and pulled them apart from each other. So this is like liquid water here. Molecules are close together, interacting strongly. And here we have gaseous water, also known as water vapor. And those molecules are moving really rapidly away from each other. All right, so let's talk about London dispersion. Let me do the example for you first. So we have two hydrogen atoms. Hydrogen is diatomic. And those two electrons are just moving around between the two hydrogen atoms. And the molecule is nonpolar. There's no electronegativity difference between either one of the hydrogens. Obviously, they're the same size. So the electrons are going to spend time equally. They are equally shared electrons. They spend time equally around each one of the hydrogens. So let's say that we have another hydrogen molecule. That one is the one in blue. And it's just kind of hanging out doing its thing. Is there any reason why these two molecules would want to be stuck together? And right now, your answer is probably no. There's no real reason why these two hydrogen molecules would want to stick together. Just keep that in mind. We're going to come back to it in a second. Okay, what about dipole-dipole interaction? So the best example I'm going to give you is HCl. Here's the full Lewis structure for this is HCl in the gas phase. It's not the acid, but this is hydrogen monochloride. This molecule is absolutely polar. Chlorine is more electronegative than hydrogen. That leaves my hydrogen as partially positive. That leaves my chlorine as partially negative. So this is a polar molecule, and it is a polar covalent bond. The electrons are shared unequally. The electrons spend more time around the chlorine. All right, so now, and I'm going to do this very, very dramatically. Let's say another HCl molecule shows up. Is there a reason for the green HCl to be attracted to the black HCl? And the answer is hell yeah. That hydrogen is partially positive. There absolutely wants to be an interaction between the partially negative chlorine of the black molecule and the partially positive H of the green molecule. That is called the dipole-dipole force, or the dipole-dipole interaction. So here is an official definition for you. Attraction between oppositely charged poles of adjacent molecules. So the partial negative of the black chlorine is attracted to the partial positive of the green HCl molecule. That's a pretty strong force. Like if you think about two different magnets, right? You bring the positive end of one magnet to the negative end of another magnet and they click together, and you have to put in force in order to pull them apart from each other. Okay. So, what about this hydrogen again then, right? I said, when you look at it, you're like, I don't know. It doesn't look like there's any reason why they would want to stick together. Well, let's say that at a given instance, it just so happens that the two electrons that are shared between the hydrogen atoms are located around the right hand. And I am talking in an instant. Remember, I don't know how I'm going to be able to show this without my hand motions. These electrons are just moving all around. They're just rotating all around. As one is going, the other is going. These electrons are just going all over the place. What if at one given instance they're located? It is instantaneous, okay? As soon as they both land on the same side, they're going to move again. It is instantaneous, but it absolutely can happen just by kind of like the laws of probability. It can just so happen that those electrons in that instant are on the right-hand hydrogen. In that instant, that right-hand hydrogen has a partial negative charge. It's got a little extra electron around it. That means the left-hand hydrogen has a little partial positive charge. This is an instantaneous dipole due to movement of electrons. As soon as it's formed, it goes away again, but it does form. So in that instant, our other hydrogen molecule is just chilling out doing its own thing, and its electrons are just like, whoa, 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 whoa. I don't want to be over there. I want to be over here. That is not a positive. Don't write that down. In a given instant, the left-hand hydrogen is partially negative because it's got the electrons around it, and the right-hand hydrogen is partially positive. There is our interaction. So the London dispersion force is by far and away the weakest, and hopefully you can see why it's the weakest. It's instantaneous. As soon as an attraction forms, it goes away again. So this is the instantaneous dipole due to the movement of electrons. Let me flesh this out a little bit. It is attraction between molecules in general. We're going to find that out. Molecules due to Instantaneous dipoles formed by movement of electrons. The biggest thing I can say about this, not only that it's the weakest, but every molecule has the London force. Every single molecule. And why does every single molecule have it? Because every single molecule has moving electrons. This attraction between adjacent molecules can form because of this instantaneous dipole. The instantaneous dipole is formed because of the movement of electrons. So every molecule that has electrons, and they all do, because molecules have bonds. Bonds are shared pairs of electrons. So every molecule has pairs of electrons in it. Every molecule has the opportunity for having an instantaneous dipole to form. Every molecule has the London force. All right. So we've got the London force. It's the weakest, formed between molecules just due to the movement of electrons. Excuse me. Dipole is the middle force, attraction between oppositely charged poles of adjacent molecules. So, which has the highest boiling point? And while you guys are looking at that, I'm actually going to Google this because oh, wait a minute. Let me just do this on my, oh, I'm a mess right now. All right. Methane. Let us do some, I'm just getting a calculator. I'm so sorry, friends. Here we go. Methane has a molar mass of 12.01 plus 4.04. So it has a molar mass of 16.05 grams per mole. That's going to be important in a minute. Butane, 12.01 times 4 plus 10 times 1.01, has a molar mass of 58.14 grams per mole. Last but not least is hexane, 16 times 12.01 plus 14 times 1.01. That has a molar mass of 86.2 grams per mole. What we need to know, okay, the question is asking which has the highest boiling point. When you're approached with this kind of problem, the best thing to do is to figure out what is the strongest intermolecular force present between two of those molecules. So when I say that, I'm talking about like when a CH4 molecule meets another CH4 molecule, how do they interact with each other? Is there an attraction? How strong is that attraction? And I'll tell you, methane is a completely non-polar molecule. It is non-polar because there's no electronegativity difference between carbon and hydrogen. So the strongest that we know about right now, the strongest intermolecular force it can possibly have is the London force. Non-polar attraction just due to movement of electrons. Butane, also non-polar. It's non-polar because, again, there's no electronegativity difference between the carbon and the hydrogen. We don't actually even really need to know what these molecules look like, but just for funsies, I'm going to draw them for you. You can double check and draw them for yourself if you want to. These are hydrocarbons. Hydrocarbons only have carbons and hydrogens. Hexane, 1, 2, 3, 4, 5, 6. And we've got hydrogens filling in all of the octets on each one of the carbons. So butane is a 4-carbon chain. Hexane is a 6-carbon chain. So the strongest intermolecular force present between two molecules of butane is the London force. And same thing with the hexane. All right, so now all we know is that the more tightly held the molecules are together, the more attraction there is between the two molecules, the higher the boiling point, because we're going to have to put in more energy to pull those molecules off from each other. It's kind of like a boyfriend and girlfriend holding hands. If they're holding hands like really, really tight to each other, you got to put in a whole bunch of energy to separate them. And it's not like you're breaking the girlfriend down into her pieces. She's still a girlfriend. He's still a boyfriend. They retain their identities. You just don't have them holding hands anymore. All right, so now, though, which one has the highest boiling point? The two molecules are held together based on instantaneous movement of electrons. And in a given instant, the electrons are in one place, giving it an instantaneous dipole. Well, my friends, this has way more electrons. There is more opportunity for instantaneous dipole formation. This is going to have the strongest London force. This will have the highest boiling point. And I'm going to look at that in a second so I actually can put the number down. Methane, on the other hand, is going to have the lowest boiling point. It's a little wee tiny molecule. It's little. There's not going to be a whole lot of movement of electrons. There's not going to be a whole lot of difference in the instantaneous dipole formation. If you've heard about this in the past, you might have heard of a term called polarizability. I'm not going to get into it, but methane is less polarizable. It's smaller. There's just not a whole lot of chances for there to be movement of electrons. So that being said, what is the boiling point of methane? Negative 162 degrees Celsius. It's a gas at room temperature. All right. So negative 162 degrees Celsius. What is the boiling point of butane? Negative 0.5 degrees Celsius. All right. Still a gas at room temperature. This is like your butane lighters, but you can see what a huge difference had happened. We went just from a molar mass of 16 to a molar mass of 58. Just that added like mass of the molecule because of the movement of electrons. This butane molecule is attracted to an adjacent butane molecule very, very strongly. There's a big attraction between those two molecules. You've got to put in a whole bunch of energy to separate the red butane from the purple butane. Again, butane stays itself. Nothing is broken in butane. You're just separating one butane molecule off of another one. Last but not least, hexane. What is the boiling point of hexane? Hexane is definitely a liquid at room temperature. It is, I don't want it in Fahrenheit. There we go, 69 degrees Celsius. Way higher. All we did was add 2 more carbons and 6 more hydrogens. Just that was enough to get the boiling point to increase so dramatically. So the stronger the London, the higher the boiling point, because the more energy is required to pull the two molecules away from each other. Now, this is fascinating to me. 1, 2, 3, 4, 5. This is pentane. This molecule is C5H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, C5H12. This molecule is 2,2-dimethyl propane. It has a molecular formula of C5H12. This has a special term. When you get to organic chemistry, this becomes really important. But these two molecules are isomers of each other. They have the same molecular formula, but different connectivity. Different connectivity. They're connected differently. So since they're connected differently, they're different molecules and they have different properties. But the question is, which one has the higher boiling point? So again, we're talking about what happens when purple pentane sees green pentane. We have an interaction. How is that interaction different between the isomer, the 2,2-dimethyl propane? How much is that interaction? Take a second. I want you guys to think about it. Which one is going to have the higher boiling point? And the answer is pentane, just straight normal pentane. will have the higher boiling point. Now I'm going to look that up for you guys in a second just to prove it to you. But this is the difference between noodles and meatballs, okay? I'm making spaghetti for dinner tonight, and I want you to think about how much energy it takes for you to go in and pick off one noodle of spaghetti. It's getting all tangled up, right? It's got that long kind of tube shape. That long tube shape can curl around all of the other tube shapes that are around it. So this is spaghetti. It is hard to pull a spaghetti noodle off of another. There's a lot of interaction. It actually comes down to surface area. There's a surface area to surface area interaction between these tubes versus these guys over here. These guys are meatballs. There's much less interaction. I mean, you can even see in my very poorly drawn diagram here, this has interaction across the entire like noodle shape. Here, we only have interaction at a small junction. So that means that there is less interaction in spherical molecules. They just can't get close enough to each other. So since they can't get close enough, they can't intertwine, that lessens the boiling point. Less energy is required to pull meatballs off of each other compared to pulling noodles off of each other. So boiling point of pentane is 36.1 degrees Celsius. And the boiling point of 2,2-dimethyl propane is 9.5 degrees Celsius. That's huge. That is huge. They're the same molecular formula. They have the same number of atoms. They have the same number of electrons. Same everything. But just based on the shape, that the 2,2-dimethylpropane is more spherical, that means that it has a lower boiling point. Less energy is required to pull the two molecules away from each other. And again, remember, the meatball stays a meatball. You're not breaking anything down within the meatball. And you can't use the spaghetti meatball analogy for everything. It just has to do with boiling point and intermolecular forces. All right. So I told you that there were three forces. I told you there was the London force, the dipole-dipole force, and then hydrogen bonding. Well, here are three different molecules. We have butane. We already looked up the boiling point of butane. Negative 0.5 degrees Celsius. C4H10. The next molecule here, let me write down that this is butane just so I reference it. This is a molecule of acetone, C3H6O. I'm going to look up its boiling point right now. Acetone. 56 degrees Celsius. And I'm going to look up the boiling point of that last molecule, which is isopropanol. This is the propanol. This is the rubbing alcohol. Boiling point of isopropyl alcohol. 82 degrees Celsius. There's a huge difference happening here again. Again, most of these guys, the molar masses are approximately the same. Okay. I know that there's going to be little differences here and there, but approximately the molar masses are the same. So it's got to be something else causing the differences in these boiling points. Butane only has the London force present. It's a non-polar molecule. Since it's nonpolar, the only interaction it's going to have with an adjacent butane molecule is the London. Acetone, polar. It is absolutely a polar molecule. So since acetone is a polar molecule, it still exhibits the London force. Okay, I really need to emphasize, it still has the London force. It's still there. You can still have instantaneous dipole formation due to the movement of electrons, no problem. But it also exhibits the dipole-dipole interaction. So it's got more to it. It's got a stronger force. That's why its boiling point is so much higher. Well, what's going on over here with isopropanol? It is absolutely a polar molecule. I'm going to redraw this. And again, I haven't talked about this, but there's a carbon at every one of these junction points, and it's got enough hydrogen atoms to fulfill its octet. So if you're like, what is she talking about? The molecular formula isn't C3H8O. It is. It is. I'm just not showing them. Let me draw it out in its full glory. Full, beautiful Lewis structure. Sorry, I'm running into that shape over there. It doesn't actually matter. There is our full Lewis structure for isopropanol. It's polar. Oxygen is more electronegative. It pulls the electron density towards itself. That leaves carbon partially positive. Oxygen is more electronegative. It pulls the electron density to itself. That leaves hydrogen as partially positive. This is nonpolar here. This is nonpolar here. But we have polar bonds. And those bonds don't cancel because that shape is bent and has a bond angle of 105 degrees. So this molecule's polar. So we know it exhibits the London force because it's a molecule. We know it exhibits the dipole-dipole force because it's a polar molecule. But why does it have such a bigger boiling point? Because it also exhibits our third force, which is called hydrogen bonding. Now, this is where I get to rant that hydrogen bonding has the worst name known to mankind. And I believe that the biologists named it this because there's no way a chemist would ever come up with this name. Hydrogen bonding is not a bond. I made a big deal at the beginning of this class to say bonds are shared pairs of electrons. Hydrogen bonding is not a bond. There's no electrons being shared. It really is just a force or an interaction between two different molecules. It is a very, very strong dipole-dipole interaction. So when you have an H, a hydrogen, bonded to fluorine, oxygen, or a nitrogen, and it is attracted to an adjacent fluorine, oxygen, or nitrogen. That's when you have the opportunity for a hydrogen bond. Very, very specific situations. So the best example, our beautiful good friend, water. Water is polar. Pulls the electron density. Oxygen is more electronegative. Oxygen is partially negative. Hydrogen is partially positive. Well, here's the thing. That's like really, really polar. When you have an H bonded to FO or N, it is a really, really, really polar bond. So when an adjacent water molecule comes in, it's got its own stuff happening, right? It is hanging out being a polar molecule all by itself before anyone panics about missing lone pairs. That oxygen is partially negative. The hydrogens are partially positive. Well, my friends, huge interaction between the adjacent molecules. That's not a bond. There is no electrons that are shared between those molecules. There is no bond. It is just a really, really strong interaction. And that is a hydrogen bond. So when you have an H bonded to FO or N and an adjacent FO or N, that is the opportunity for hydrogen bonding. So here's your summary slide. All right. So just, again, take a pause, write it down. London force, also known as the instantaneous dipole force or the dispersion force, in case you read about that. It is the attraction between molecules as a result of instantaneous electron polarization, instantaneous movement of electrons. It exists between all molecules. The dipole-dipole force is the attraction between oppositely charged poles of adjacent polar molecules. And hydrogen bonding is the attraction between an H bonded to fluorine, oxygen, or nitrogen and an adjacent fluorine, oxygen, or nitrogen. So, here are the implications. The stronger the intermolecular force, and again, take a second, I want you to think about it in your head. Is the boiling point going to go up if they're strongly held together, or is the boiling point going to go down if they're held strongly together? Stronger the intermolecular force, the larger the boiling point. You're trying to pull two molecules away from each other to go into the gas phase. You got to put in a whole bunch of energy to pull molecules away from each other if they're held together tightly. So the stronger the intermolecular force, the larger the boiling point. The stronger the intermolecular force, how readily will it evaporate? So if two molecules are held strongly together, are they going to evaporate quickly, go into the gas phase quickly, or are they going to go and evaporate more slowly? The stronger the intermolecular force, the less readily it evaporates. It wants to stay together, so it's not going to evaporate very quickly. This I'm going to get rid of because it's lab specific. So if you're doing this kind of lab, then more power to you. Because of this weather, I'm not entirely sure. So I will deal with the change in temperature in lab if that becomes necessary. All right, more implications. The stronger the intermolecular force, what do you think about the vapor pressure? The vapor pressure it's like if you have a beaker with some kind of substance in it, liquid or whatever. How much vapor is in the gas phase above it? So if a molecule is held really, really tightly together, are you going to get more vapor or are you going to get less vapor? The stronger the intermolecular force, the lower the vapor pressure at room temperature. It just wants to stay together. It doesn't want to go into the gas phase at all. So you're going to have a lower vapor pressure. And again, I'm going to skip out on this because it has more to do with what's coming up next. And so I'm just going to leave that alone for right now. All right. So another implication, like we talked about, is solubility. And that is like dissolves like. And I want you guys to know this is much, much more complicated than I'm about to tell you. So when you get to organic chemistry and the organic chemistry professor starts talking about solubility, you can't say, oh, Dr. L told us this. She was wrong. I'm not wrong. I am just way simplifying things for this class. This is much more nuanced than what I'm about to tell you. I am simplifying it. There are a lot more complications. If you carry on in chemistry, just keep in mind there's a lot of nuance in solubility. But for this class, for our general purposes right now, like dissolves like. If two molecules have the same strongest intermolecular force, they will be soluble in each other. So let's take a step back. Here's water. What is the strongest intermolecular force present between two molecules of water? The strongest intermolecular force present is hydrogen bonding. The molecule exhibits the London force because all molecules do. Water is polar, so it also exhibits the dipole-dipole force. And finally, we have H bonded to F, O, or N, so we have the opportunity for hydrogen bonding. Here's that molecule of ethanol that we talked about previously. Again, I'm drawing this not showing shape, just so you're aware, but here's a molecule of ethanol. What is the strongest intermolecular force present between two molecules of ethanol? Well, it exhibits the London force. It also exhibits the dipole-dipole force because it's polar. Again, even though I drew it badly, that polar bond and that polar bond, they don't actually cancel. I can't leave it. I can't leave it. I'm going to draw it showing shape because it's bent, remember? There we go. I couldn't do it. I tried. There it is showing shape because this is bent. So this molecule is polar, so it exhibits the dipole-dipole force. And we have an H bonded to F or N. That means it's going to be attracted to an adjacent an adjacent F or N. So this molecule also exhibits hydrogen bonding. Ethanol is soluble in water. They have the same strongest intermolecular force. What about dichloromethane? That was the other example that we did when I talked about it previously. I'm kind of sort of showing shape, not very carefully. But we said that this molecule was polar because the chlorine is more electronegative. So, what's the strongest intermolecular force? It exhibits the London force. It also exhibits the dipole-dipole force. This molecule is not soluble in water because water is hydrogen bonding. Dichloromethane is just dipole-dipole. I just had a few other things I wanted to talk about. I'm just going to kind of skip through this a little bit to get to my favorite thing, mostly because my dog is about to start barking because she has to go to the bathroom. But this whole idea of intermolecular forces can really help you understand things in biology. Oh, she's going to start crying. We have a fatty acid. A fatty acid has a polar part of the molecule and an opportunity for hydrogen bonding. But over here, this is super nonpolar. The vast majority of this molecule is nonpolar and hydrophobic. It just has a teeny tiny portion that is polar and hydrophilic. So because of that, you form these things called micelles. That's how soap works. More importantly for biology, it is the phospholipid bilayer. Bum, bum, bum. These phospholipid bilayers have a polar head on them. So this is the polar head, and it's got these non-polar tails. So they arrange themselves in what is, and I'm sure if you've taken biology before, they've talked about the phospholipid bilayer. Extracellular is watery, but you have this non-polar like middle that forms itself. And so that's how we have the phospholipid bilayer of the cells. Significantly more fascinating to me. Hydrogen bonding is so important. It is the only thing holding our double-stranded DNA together. So hopefully you guys know DNA is double-stranded and it's held together only via hydrogen bonds. So hopefully you've learned, or if you haven't, maybe you'll learn in the future. Base pair G always goes with base pair C. And the reason for that is because of hydrogen bondings. We have an H bonded to FO or N, and it is adjacent. It is attracted to the adjacent oxygen. That's a hydrogen bond. We have an H bonded to FO or N, and it's attracted to an adjacent N. H bonded to FO or N and an adjacent O. And you can see they are perfectly lined up. G and C are always going to come next to each other because of the way it's aligned. A and T always go next to each other again for the same reason. And so the only thing holding our DNA together is hydrogen bonds. And that's because we need to be able to go in there and pull the two strands apart for RNA, blah, blah, blah. Then they need to come back together. So it actually does need to be held together relatively tightly, but also so that it can be pulled apart from each other. These interactions are also really important for protein structure folding to make enzymes. And my absolute favorite is snowflakes. The reason why snowflakes will always have 6 points is because of hydrogen bonding. And the reason I think this is so cool, we can't see water molecules. We can't see that bent shape. We can't see an interaction between two of them, right? Like unless we had like, a microscope, quote unquote. But what we can't see on the molecular level, as it gets up into ice crystals that we can see in the macro level, we can see the implications of that hydrogen bond, the way the molecule is shaped, the way the water molecules interact with each other will always give us six-sided features of our snowflakes. All right, friends, that is the end of this first chunk of material on intermolecular forces. Thanks for hanging out. I will catch you in the next one.